So I think it's working. Can everybody see? All I see is the placeholder, but I think that's intentional on their part. Yeah, both of those are quite nice for trying to deliver content. And really, what more is there to life than trying to deliver content? I think there is about a 30-second delay, though. So feel free to ask questions in the chat box with that delay in mind. I will respond to it in probably a minute. All right, we'll just give it a second for more people to filter on in. I have not turned it to low. I don't know if I can do that in the middle of the stream, but let's see if this will work. Nope. I'll have to change it next time. All right. So I think we can go ahead and get started. So, what we're going to talk about today is a survey of numerical methods for dynamical systems, because that's generally what we care about as people who study the world and try to model the world. Some of us are interested in things that don't change, those sort of static equilibrium systems. But a lot of us are on the other end of things trying to figure out what's changing, what's going on. And so we're going to look at our different a different collection of methods for these type systems. And first we're going to talk about the introduction, why we're bothering with this seminar series in the first place, and why I thought it would be a good idea to do it, and sort of my background that sort of lets me feel relatively confident about actually doing this seminar, just relatively. All right, then we'll talk about our different kind of models for our dynamical systems, a couple different types of equations. And then we'll work an example. And I've actually swapped out the example because if we tried the in-body problem as the example here, it wouldn't take 20 minutes. It would probably take an hour and a half. So I figured it would be a better choice if we start a little bit smaller. In grad school, I had the reputation in our research group of always biting off much more than I could chew, and then spending 3 weeks solving a test problem because I picked one that was too difficult. Start small and build up. So we're trying to fix that now. All right, but we'll start with an introduction. And so the motivation for this seminar series and all the different talks we're going to have in it is that I taught a statistics for engineering course, all right, to a bunch of mechanical engineers, and then I have a statistics for scientists and engineers course for computer scientists and our general science majors, and then our electrical and civil engineers. So I've got a bunch of engineers in the past. And something I noticed after those engineers would graduate, leave my class, do well in it, leave my class, is they'd get to their other classes, their dynamics classes, their laboratory classes, things like that, and they would need a rather large variety of additional tools that were kind of assumed knowledge. There are things that you kind of need to know, but no one has time to teach you, right? How to integrate an ODE numerically, how to solve a nonlinear system of equations numerically. So people would come in and look at, they would show me these massive double pendulum equations and say, well, how do you solve this? And I would say, well, have you tried prayer? And they didn't like that answer. So they said, is there a way we can do this maybe in MATLAB, maybe in something else to allow us to solve these problems? All right, and the answer was yes. I had experience solving these dynamical systems in the past. So working together, we could kind of get a solution to that. But so many kept coming. It wasn't just a few. It was probably like 8 or 9 that I've had come and solve similar type problems. But I thought, let's just do a seminar series on these topics, so that you can we can have a recorded sort of repository of here's how to deal with these problems. All right, and so we'll take a look at all these sorts of things, and we'll flash back and forth to the topics page. Today we're doing a survey of all the lay of the land, and then we'll delve more deeply into all the different sort of topics that we're going to cover. So my background is in computational astrophysics, all right? And I've also done a little bit of other stuff here and there, agent-based epidemiology models. I have a couple papers on laser beamline modeling, trying to model how laser beams behave in these very advanced sort of optical networks and things like that. But the bread and butter of what I do is essentially computational astrophysics modeling, right? And those systems are very, very dynamic, right? Things happen in space. Violent, massive, explosive events are happening all the time somewhere. And so using dynamical systems and our tools for modeling those dynamical systems is very important in those astrophysical contexts. All right, so here we have a couple experiments, numerical experiments I've carried out before, where we shoot a laser at the end of this. Let me see if I can't sketch. I'm not used to not having my tools. We shoot a laser here at the side of a foam, all right, and then we shoot a blast wave into that, which causes these fluid instabilities, these hydrodynamic instabilities to form at the interface between this plastic and this foam as this laser blast wave propagates through the medium. Very, very dynamic, right? Explosive, blast wave, things like that, lasers, a lot going on. I've also looked at sort of the interiors of stellar atmospheres, trying to model the sort of boiling over behavior of those different layers and seeing what kind of turbulent eddies we get penetrating from relatively stable layers, into relatively stable layers from these very dynamic layers. So that's my background, and why I like dynamic systems and why I like talking about them, which is why you're now listening to me talk about them. But I want to just flash out essentially my grad school experience in 4 equations, right? This is the set of equations, a subset of the set of equations, but the main thrust of the set of equations that I modeled as part of my dissertation, right? And so I looked at these set of equations, and I solved these set of equations for certain conditions. And then, as part of my dissertation, I asked myself, how can we make this set of equations here more difficult? How can we really screw ourselves over and give ourselves an even harder set of equations to solve? So I would look at something like this and say, oh, you see this coefficient right here? Let's change that from a coefficient. Let's make that a tensor, right? And then all the nightmare that ensued from making that a tensor I would work on. Same thing with this coefficient right here. I'm like, that could be a tensor too. Let's make everything a tensor. Why not? Right? And so my dissertation is on how do you actually solve this system of equations when it goes from this nightmare fuel right here to something even worse, right? And so you can't just use your out-of-the-box toolkits for solving those sort of systems of equations when you've made them into this sort of tensor nightmare. So that's my background. That's what my dissertation is. And these are the equations that govern the dynamics of plasmas operating in high density and high temperature environments. All right, you've got density here, you've got the velocity field, you've got the magnetic field, you've got the internal energy, you've got the temperature. And so this says, when we have this sort of plasma thingy rolling about and all, what happens to the temperature distribution, what happens to the magnetic field distribution, and so on. How does it grow, how does it decay, things like that. So my job was to solve this, and that's what we were looking at when we were doing these scenarios. When did we get magnetic fields growing in here, and could that possibly lead to certain interesting astrophysical phenomena like supernova and whatnot? So that's my background. And those systems, those are dynamic, right? And so we're going to talk, that's why I feel somewhat qualified to answer questions about dynamical systems, because I spent way too long thinking about this set of equations here and how to handle all the individual terms. So I want to start with essentially laying out what this talk is. This talk is not designed to equip you to run out and solve this system of plasma equations. All right. After an hour, you're not going to run out and be able to say, "Oh, I can handle all this. Let me just integrate that forward in time, and boom, supernova." No, that's not what we're after today. Right? We have all of these other talks coming up. Let's see if I can't pull them up. All of these other talks that will give you a piece of the puzzle. Right? Numerical linear algebra in MATLAB, finite difference boundary value problems in MATLAB, and so on, to give you a piece of the puzzle to fill in and essentially look at those individual terms and solve them. So instead of doing that, trying to cram that all into one talk, because it's not possible, what we're going to do is we're going to do a survey of the different methods out there and talk about when we might use them, the advantages and disadvantages of the different methods, all the different subproblems that those methods sort of lead to, right? Those methods don't just spit out an answer. They give you a new problem, which you have a tool to solve. And that tool might give you a new problem, which you have a tool to solve. But eventually, after you've done that recursively enough, you've got an answer. But most importantly, what I want you to get from this talk is to think about essentially the thought process that goes into the development of these methods, right? Oftentimes, when we encounter these difficult sets of equations right here, the first blush is to just give up. We can't deal with that. That's too complicated. But numerical analysis and scientific, computational scientists and whatnot, they look at those and they say, how can we change the game a little bit? How can we change that equation to make it something that I can handle without going insane? And so that's what they do. And I want you to take away when we look at these methods, what sort of decisions are made to make that from a problem that we can't solve to one that we can. So I'm just going to essentially give you the rationale for all these different sorts of methods that exist out there. And I'm not going to be able to cover them all because I'm already probably going to go over in time. We've got 33 slides here, so this should only take about 2 hours if my dissertation is any indication. But we'll try to go as fast as we can through these. So, when I say dynamical systems, I mean something specific, right? When a physicist or a mathematician says dynamical systems, they each mean something slightly different, but close enough for our purposes so that we can essentially treat them as the same thing. So when I'm talking about a system that is dynamical or dynamic, I'm saying it exhibits some time-dependent behavior. We've got some variables that define the state of our system. That could be the temperature of the thing, or the density of the thing, or the position of the thing, or whatever. Just some variables of state that undergo change with time. Right? And so with that claim, oh, this quantity is undergoing change in time, we can do a little bit of sleight of hand. We can change the problem a little bit. Right? We can say, well, if they're undergoing change in time, that implies there's some non-zero time derivative, right? So we can use time derivatives as our sort of stand-in, what we can put in as the sort of, this is the thing we're trying to model, the time derivative of this thing, right? And we're going to contrast those type systems with what we call dynamic systems are going to be contrasted with our steady state systems, or our static systems, or our systems at equilibrium. Those are just staying the same. They have a zero time derivative. Nothing changes. Once you're stuck with a zero time derivative, absent some outside force, because the state variables don't change anymore, they can't change the derivative. Once you're in that steady state, outside something else going on, you're stuck in that steady state. So we're going to look at those purely non-zero time derivatives. So I've tricked you. I have lied. I've promised you a survey of numerical methods for dynamical systems, and what I've decided to give you instead is a survey of numerical methods for differential equations, right? Because if we can describe that time derivative as a set of as an algebraic expression, we can describe our system as a differential equation. And if we can solve those differential equations numerically, we can model the behavior of that system that derivative is designed to capture. So by doing that sort of rhetorical sleight of hand, when I go, oh, we're going to model dynamical systems, no, we're going to model differential equations, using the fact that that time derivative is 0, that bridges the gap between dynamical systems and differential equations. And so we have the perfect mathematical toolbox for solving these systems. And I'm sure you guys have noticed that when you get those double pendulums and everything, you're like, this is a very nasty differential equation. If you're lucky, it's a differential equation. You might be stuck with a differential algebraic set of equations or a differential system of equations or anything like that. So we're going to look at the tools to solve those differential equations such that we can map those solutions of those differential equations over to the solutions then to model the behavior of our dynamical system. All right, so first we need to be able to differentiate different differential equations. Right? And what I mean by that is not all differential equations are made the same. They exhibit different behaviors, and because they exhibit those different behaviors, we need to have different tools to capture those. All right? So the first set of differential equations we're going to consider are the ordinary differential equations. And all that means, those ordinary differential equations, is that we have ordinary derivatives in them. The only derivatives we care about are ordinary derivatives, right? Contrasting that with a set of partial derivatives, right? And so the only variable I'm taking derivatives with respect to in all of these equations, this system of equations here, is time, right? This set of equations right here is called the Lorentz system. And it's a relatively simple system of equations that actually exhibits chaotic behavior. This is one of those quintessential chaotic examples of chaotic system. All right, but even though this is a chaotic system that has a lot of, the behavior is very, very sensitive and it's hard to model this thing well, we only see time derivatives. Even though we've got 3 variables of state, x, y, and z, and even though that they're coupled, y appears in the x differential equation, x appears in the y one, and so on. Even though that's the case, we only care about derivatives in time. And so we use that regular d, and so we indicate we have an ordinary derivative. So this is a set of ordinary differential equations. Contrast that with equations that have these partial derivatives in them. Right? So we have partial rho with respect, partial t. That's saying the partial derivative of density in this case with respect to time. Right? Which means there are other dimensions that I'm going to be taking derivatives in, such as under this operator. This divergence operator is essentially the x derivative. So we've got a partial rho with respect to t, and we've also got a partial rho u with respect to partial x, right? So we have a series, in this case just a single differential equation, but we can also have a system of partial differential equations. They're all very coupled. And that was the ones I was working on. I was working on these partial differential equations, all these partial derivatives, right? Where we have these divergences and these curls. Those are spatial operators. Those operate in the x, y, and z realm. All right, so we had multiple derivatives in multiple dimensions. So when you're looking at the system you're trying to solve, and you realize that you can use the Latin alphabet, you can use your Latin Ds, you're okay. You can use you're in ordinary differential equations. It's not so bad. Sure, they can get chaotic. Sure, they can get hairy. Sure, you have systems and nonlinear things. But, when you're using the Latin D, everything's pretty much okay. When you have this Greek, when you have to rely on the Greek D for those partial derivatives, things will get very ugly very fast because you've got derivatives in x, y, z, t, and all sorts of other dimensions, depending on the dimensionality of your problem. All right, so those are the 2 types, and those 2 types are going to lead us to vastly different methods for solving. So first we're going to look at, and we're going to have a whole talk on this. Well, actually, let's talk about what it means to ask a good question. So we'll have a number of methods to solve these different type problems, and that's what we're going to cover today. But don't think because you have a problem and you have a method to solve it that you can solve the problem. Those 2 things alone are not enough to solve the problem. You also need to essentially give the problem an environment to live in. right? Where is this problem happening out? How does this problem start out? So in order to actually solve these problems, you always need to make sure it's well posed by ensuring it has the adequate starting material so that you can actually use the method. So the first thing, the thing that we're always going to need, is some domain, right? We need to ask ourselves, what values of space and time are we trying to model the system over? What values of space and time do I actually want to have the answer at? Do I just want the answer at the very end, or do I want intermediate answers to see how this behavior evolves over time, right? Do I want to use that on some sort of grid, or am I going to use some gridless method? Right? So that's the domain. Where am I working on, and what points do I want to answer this question at? You will also generally need initial values. Like, how is the system starting out? If I don't know how the system's behaving at the beginning when I start modeling it, what the system looks like, how can I possibly answer what it's going to look like? You don't have that information, so you need those initial values as well. And then finally, you need to ask, well, what happens when the domain ends? What happens at the end of my domain? What happens at the points that are outside, at the interface between the points I don't care about and the points I do? Because those can affect your system. How am I going to treat those boundaries is what we call. All right? So when we're dealing with those nasty PDEs, because we have those extra derivatives, we generally need both initial values for our state variables and boundary values or boundary conditions. What happens at the end of my domain? Whereas in ODEs, I can either have an initial value set and solve what's called an initial value problem, or I can have a boundary value set and solve what's called a boundary value problem. So let's take a look at what a domain might look like. All right, so this is my bread and butter once again. This is a rectangular grid, right? Nothing too fancy. All I'm saying is, look, I have two dimensions, x and y, and I want to model the behavior of some system, maybe the heat equation to solve how hot the points get, in relation to one another, maybe some stress equation, maybe some fluid flow equation, and I want to solve it from 0 to 1 in y and 0 to 1 in x. So I'm going to create some grid, point here, point here, point here, that I'll essentially constrain my solution to, right? I'm going to say I want my solution to be accessible at these points. I might not be able to answer what happens in the middle of these squares, but at least I can answer what's going on at the corners. And if I make the point small enough, there are enough corners, I'm happy with my solution. Right? So that's the domain we've set up here. We've got the limits, and we've got the points on the interior of it. But we've also got boundary points. We need to essentially say what happens when we've run out of points to consider. We're at the edge of our boundary. So we need to specify that for our systems. So once again, as I'm going through this, you can ask questions, but there is about that 30-second latency. So you can ask questions in the chat, and I'll see it, and then when I have another monitor over here. So I can see your questions, and when I get to a natural stopping point, I can address those questions. So what we're going to need to make the problem well posed. A problem, a dynamical system of equations, plus a method will not give you a solution. You need additionally, where do I want that solution at, and what's the starting point of the problem. All right, so we're going to start talking about methods for ODEs and systems first. ODEs are very simple, and I'm actually not going to spend very much time talking about this because we have an entire dedicated talk on ODE systems. Yeah, Odes to Joy, techniques for numerical solutions to ODEs. So I'm only going to outline the most basic of the numerical ODE solution today, and if you want further information about that, we'll essentially talk about that on this next talk, not next necessarily, but when we get to Odes to Joy, techniques for numerical solutions of ODEs. All right, so dynamical ODEs are usually given as initial value problems, where they don't give you the boundaries, they give you the initial value, what happens at the beginning of the system. There are some exceptions to that. There's something called the shooting method, which treats a dynamical system as a boundary value problem. But let's focus on the sort of general case of I've got an ODE that's described as some sort of initial value problem. So I've got here a derivative. This is the equivalent to, once again, I'm not used to not having my annotation tools. I can't draw on here. I've got this this derivative, an ordinary derivative with respect to time, is equal to some function, and I want to solve for the behavior of that y. I want to know what happens to y, and all I know is what happens to its derivative. And yes, I have dropped a parentheses. Right? So understanding what happens to the derivative, can I say what happens to the value itself? So an analogous example of this would be, say, I know the velocity of something as a function. Can I describe its position in time? I know how fast it's going. Can I say where it goes, how far it goes? Well, the answer to that question is yes, as long as you know where it started. So you need this initial condition, right? You need the solution at your initial time, right? We can then essentially do everybody's least favorite thing and say, hey, what if I take the Taylor series of my thing, right? What if I take the Taylor series from my initial starting place, my initial starting place, and just expand about that initial starting place? All right, and so you would then say, well, the position after a certain amount of time, after you've gone a little bit in time, is equal to the position at the starting place plus all of your Taylor series terms. All right, the derivative of your function at that starting place divided by 1 factorial times the time step plus the second derivative at the starting place divided by 2 factorial times the time step squared plus the third derivative divided by 3, and so on and so forth forever infinity. Right? Now, we're not going to use the full Taylor series. What do we do as engineers and physicists and whatnot? We say 2 terms is good enough, right? The first order term, the term with just the time step, is good enough, and we're good to go. So then what we can do is essentially we can solve for this y prime, right? In terms of delta t and the initial conditions. So we can rewrite this set of equations, this one right here, I'll go back, come on, go back. We can rewrite this after solving for y prime as this. Y prime is equal to the Taylor series solution for y prime, which is y at the initial time, the initial starting position, minus the slightly advanced position divided by the time step. So that's y prime. And then just plugging that into the initial value problem, we get the change in starting in position divided by the change in time is equal to that function that we specify. Right? And we know the starting position because that's our initial value. We choose our time step, and we can evaluate that arbitrary function. We can solve for the position after a certain amount of time. We can solve for the new position after a slight advance. And then we can take that as our new position and find the position that's slightly advanced even more. And then slightly advance it even more, even more, even more, just delta t at a time. Right? And this was through that Taylor series expansion. This gives us the simplest of our explicit ODE integrators. We call this forward Euler. And we'll look at this at the example at the end of the talk today. We're doing all right on time. So just using that Taylor series expansion and saying, I'm not going to use the actual definition of the derivative, y prime. I'm going to substitute an approximate derivative, which is the change in y over the change in t. I now have a problem that I can solve just algebraically, one step at a time. And that gives you the ability to solve this thing. And you can model that dynamic solution, and you get an approximate numeric solution. Now, why is it approximate? Why is this not the exact solution to this thing? That would be a question I would ask you if we didn't have 30 seconds of latency. But the answer to that question is essentially because we didn't use all the terms of the Taylor series, right? This equation is only true when we use the infinite number of terms, right? But it's approximately true when we truncate it and choose a small delta t, because delta t is our choice. So if we make delta t super small, these terms get vanishingly small. They don't go away entirely, but they get tinier and tinier and tinier. And as delta t goes to 0, they do go away. And so that's what we call that our discretization error. We've taken the exact equation here, truncated a Taylor series representation of it, and solved that truncated version, and we have an approximate solution, a numerical solution to that. That we can just tell our computer, do that 1,000 times, or 100,000 times, or so on. All right, so there are a lot of relevant subproblems to this, especially when you have systems. These explicit integrators are useful, especially as sort of a building off point so you can understand how the packages that you use in MATLAB work, but they're not terribly robust. They will break if you try to take too big of a jump. If you bite off more than you can chew, they'll explode. The solution will diverge to infinity. So they're also not terribly accurate when we have such a simple system. But by using that sort of, all we did there was say, we can't do it exactly, we can't exactly handle this derivative. Let's approximately handle this derivative using our finite difference expansion here, our Taylor series expansion. Let's do that. And that is how essentially all of these different ODE schemes work. And so when we actually get to the ODE talk, we'll look at all the different versions of these ODE solvers. But that's just the simplest version, and when we get that, we might just be able to solve it for a simple single equation like that. But when you have a system of equations, you're going to get a linear algebra problem out of your ODE integrator. Or if you have what's called an implicit scheme, you're going to get a linear algebra problem. So we need to turn to those numerical linear algebra methods that we're going to cover in a different talk to essentially say, all right, well now we've reduced it to a numerical linear algebra problem. Let's solve the numerical linear algebra problem, right? Or if you have a nonlinear ODE, you might need to do some root finding. Or if you have an implicit method again, you might need to do some root finding or nonlinear equation solving. So these are the problems that you'll need to be able to handle if you decide I'm going to use this approximation to solve that ODE. And that's essentially all I have to say for ODEs right now, because once again, we're going to have the full talk on that. And we'll cover all the stuff like how big can my time step be, how accurate is my solution, what kind of problems will this work on, how do I get it for systems to work. That's all going to come in its own talk. But now I'm going to move on to essentially a survey of partial differential equation methods and give you the rationale, how they cheated the system, how they changed the problem to one they couldn't solve, well, from one they couldn't solve to one they could. All right, and we're going to start with finite difference methods. And these are fantastic as an incredibly intuitive way to handle our derivatives. And we just say, make them differences, make them slopes. Make them approximate slopes. So anyone with a familiarity with just basic calculus can handle these finite difference methods. Right? They can grasp and they can understand the intuition and the motivation. All right, so let's consider an example problem here. Right? A 1D initial value boundary value problem that says the time derivative of some quantity, I've mixed my D's there, I'm sorry, but the time derivative, partial time derivative, is equal to the second derivative in my spatial dimension. All right, and I've got the domain set from 0 to 1, and I've got my initial conditions, or these actually are my boundary conditions, from 0 to t, and from 1 to t, 0 at my boundaries. All right? Now, through the Taylor series in time, I can essentially say, all right, my solution at any given x, advanced slightly in time, is equal to my solution at the initial time, at that position in x, times that derivative, same sort of thing in the forward Euler method for that ODE. Right? And so we can ignore all these higher order terms and then just say, look, instead of dealing with that partial derivative, which, yikes, can't manage, don't want to, I'm just going to replace it with the change in my solution at a given point over time divided by the change in time. I'm going to divide it by that change in t. Right? And that's doing that in time, and doing that, you can do the exact same derivative in space. In this case, we want the second derivative using the Taylor series expansion again. We can get a system of algebraic equations instead of these partial differential equations. So the logic there is just, I cannot handle these partial derivatives. I'm going to replace them with some sort of small, finite difference in time. It's just a slope. It's all we can handle. I know what you're saying here, too. Everybody hates the Taylor series. You're saying this is intuitive, this is easy, we can do this. And it is. So you have to promise not to hate me, but essentially, the finite difference method can be summed up in this next slide. Right? we might have a second partial derivative in terms of space, a regular derivative in terms of time, a partial derivative in terms of time. Don't worry about that. Don't think about that. Don't even try to manage it. All right. What you're going to do instead is you're just going to replace it with differences in your state variables over small steps in time. Right? That's all you need to do. Instead of thinking about the tangent line, which you cannot get at accurately, replace it with that secant line. Right? Replace it with that approximation to the tangent line. And if you do that for all of your derivatives in your thing, you have what's called the finite difference discretization of that. And that's just going to give you a series of these type of algebraic equations, where this is what you don't know, this is what you do know, and this is something you choose. And so you could then just solve for the thing you don't know, and you've got your solution to that system of partial differential equations. And so we call that the finite difference method. All we do is we plug in those finite difference approximations for the derivatives. No tangents, use the secants. That's really what it boils down to. Use that approximate derivative instead. All right, the upsides to this are it's very simple conceptually. Once again, all you need is calculus 1 essentially to handle this, and a little bit of knowledge of partial derivatives, but no vector calculus really. And it's very easy to implement. And we'll look at an implementation of that in a different talk. All right. The downsides of this is it's unstable in quite a few systems. You try to use this for the wrong kind of fluid flow, and the solution blows up. Right? If you're not careful with it, the thing can explode. Right? Additionally, it's hard to make this work in this arbitrary geometry because you have to have all those points on your domain to calculate those derivatives at. All right? And this, when you do this for a large number of points, because you need to, because you have that number of derivatives you want to approximate discretely, you can end up with a numerical linear algebra problem. And you also, if it's a nonlinear problem, you might end up with a nonlinear equation solving problem. So we can cook this up as a finite difference problem and reduce it to just a matrix solve, or a root finding problem, which is something we'll cover in different classes. We're going to cover finite difference and boundary value problems in MATLAB, and we'll use that in addition to our numerical linear algebra in MATLAB. Right, in fact, it is correct to assume. In fact, our errors, the things we've neglected, are a function. The Taylor series terms here are a function of your step size. The larger the step you take, the larger the terms we've neglected, the larger your discretization error, which leads to higher inaccuracies. And in fact, when we cover these topics in depth, we'll look at what's called stability criteria, which says if you choose a time step any larger than some set value, not only will your solution be accurate, it will be infinitely inaccurate. It will blow up. When I say it blows up, I mean the error goes to infinity, which is no good, right? When someone asks you, what's the error that you solved this with, and you say, oh, the error is infinitely high, they're probably not going to trust your solution that much. So yes, those time steps are important to make those small, but you also don't want to do a billion of them, because then your computer has to do a billion different things. All right. So that's finite difference approximations, and they give us the subproblems of numerical linear algebra and nonlinear equation solving. And I like this as an introduction to these type PDEs because it's conceptually very simple. Just plug in those approximate slopes for the actual slopes, and you can solve the system through a series of algebraic equations. Very nice. But once again, it doesn't work for everything. We got to use other stuff for other things, right? And one thing, like I said, if you try to use the wrong finite difference scheme for fluid flow, it will explode and your error will be infinite, right? So something they use to fix that, another scheme they use that is stable, that will not have infinite errors, is called the finite volume scheme. And this finite volume scheme is my bread and butter. This is what I solved most of those equations with that we looked at the beginning of the slides, right? And the finite volume scheme works up by partitioning the domain into little blocks. Right? Little parcels, little cells, little countries even, if you like. And we talk about the behavior of that little block, right, as a fixed quantity. Right? Then it makes use of the fact that the changes in the state variables in that little block is, in the absence of a source term, going to be entirely defined by the flux moving across the cell boundaries. Right? And so this is what I worked on in grad school for the most part. And so I want to give you sort of a little example All right, so let's take an example where I have a country. All right, and we'll call this country Blockistan. And I want to model the time-dependent behavior of the population of Blockistan, right? So I want to essentially model the partial derivative with respect to time of P. Now, how does the population of Blockistan change? Right? Let's ignore everything going on in Blockistan, talking about how it changes, and think about, well, what can happen at the boundaries of this block? Well, you can have people leaving this block. You can have people coming into this block across all of your different borders, right? So that's one way you can have essentially the change of the population of this block. Things come in, things go out. And so if you look at the net, not the individual terms, but the net change, you can get the change across each border of this thing. And that would give you an approximate solution to the change in the population of this block. Now, that's not the only thing that changes the population here. Additionally, what else might be happening? Once again, that'd be a question I would ask if you guys had time to answer it. So we can also look at a function that describes the birth rate and the death rate. So we'll call that some function. Let's do that in a different color. F of x of t. And that gives you the change in the birth and the deaths. The people coming in and coming out, not through the boundaries, but on the inside. And so modeling the behavior of the births and the deaths in conjunction with all the people leaving and coming across the boundaries gives you the change in the population exactly. And that's the theory, that's the logic behind the finite volume scheme. I just break my domain up into a bunch of little blocks, and I see what goes on inside the blocks in terms of a source term, who's being born and who's dying, and who's leaving across the blocks. Right? And I don't know that we want to have time for the derivation of that, but that's essentially the logic of it. Right? That's essentially how we compute those. And we can do a whole nother talk on this topic. It's not on the list right now, but it's very conceptually simple. It's just I've got my finite volume, who leaves across the boundary of the volume, and who's born or dies in the volume. The other big advantage, why this is used in a lot of conservation laws, conservation of energy, conservation of momentum, is if I've got a bunch of little blocks, from Blockistan to Squaristan, say for example, I'm modeling the fact that anyone who leaves across this border from Blockistan and goes away from this population is then counted in Squaristan's population. Right? And so I'm conserving my total population by design. Finite difference will not do that. It will not fix your population if you try to use a finite volume scheme for this. It's not conservative. But because I'm going across boundaries, and so if anyone who leaves across this boundary must be entering across this boundary for this country, I'm conserving the state variable quantity here. That is fixed. And so it's very, very useful for conservation laws, which is important because conservation laws are the way the universe works. All right, the downsides are that border control work. Calculating those fluxes is not a trivial task. Asking how much fluid has flown across his face is not a simple question to ask, because it depends on the geometry of the face plus the fluid flow behavior. It's also difficult to make work on arbitrary geometries. People have solutions for this in all sorts of different geometries, but keeping track of essentially your borders becomes difficult when the borders become very arbitrary and very irregular. So this gives you a whole mesh of different subproblems. Numerical linear algebra subproblems, nonlinear equation solving subproblems, ODE subproblems, interpolation subproblems, all sorts of those things are things you need to be able to do to solve the more advanced cases of these finite volume schemes. And so this is what I use. So if we want to have a whole talk on that, I can derive these things for you. I can show you using the divergence theorem, Gauss's law, why they work. But they're very nice, simple. They make conceptual sense, and they conserve our quantities by design. So I don't want to give anyone PTSD, but the next thing we're going to look at are finite element methods. Right? And these are very interesting because they were essentially stumbled upon by a group of engineers who are using some heuristics. Let's just make a lattice of these things here, of these elements, these springs. And it turns out they discovered a gold mine, right? Mathematicians came along later and said, these finite element methods with all these springs that these engineers are using is brilliant. We can build a huge sort of mathematical foundation for it, and we can use it for basically anything. So finite element methods are the most commonly used methods for solving partial differential equations, to solve those dynamical systems. They use it for loading problems. They use it for simulations of bridges and buildings and aerodynamics, wing stress loads and stuff. If you're going to be doing dynamical systems, you're probably going to be using some finite element method. All right? And these things have such a strong mathematical foundation that they are applicable to a huge number of problems. Right? More than finite volume, more than finite difference. Right? So I know most of you know how to solve finite element methods. Right? But I want to talk about, in say 10 minutes, maybe less than that, maybe 5, the trick they use, right? Not how to solve them, but why these work. All right? So essentially, when given a boundary value problem, I know this is not dynamical, but I don't want to think about two derivatives in finite difference finite element, because finite element is already enough of a nightmare. I can't even spell it right. Right? Given a problem, the mathematicians and the engineers using this essentially give up. They're saying, I can no longer solve this exact equation in a continuous sense. I can't find a u that satisfies this equation at every x. So what I'm going to do instead is integrate and solve in an average sense, right, over my domain. I want this to hold in some average sense. Right? And there should be a v here, right? The v, it doesn't really matter, but there should be a v on this side as well. And then we're going to multiply both sides by some arbitrary weight function, v. So multiply this side's integral by v, multiply this side's integral by v. And v is just some weight function. It's something we just, here it is. So doing the integration here, solving it in an average sense, a weak sense, gives you quite a bit of a boost, and so we can start thinking about solving it. But the real reason this works is because mathematicians have figured out all the assumptions they can load v with to essentially let themselves reduce this problem into a solvable one. Right? They say, oh, v has two derivatives and its square interval, and all they really do is they say, let's load v with a bunch of assumptions that forces this integral to behave in a certain way that allows us to solve that integral and solve for the system's behavior. So the real magic of FEM happens to, there's that v, it's on this one, happens to all of the assumptions we put on our function v. All those assumptions of the behavior of the function. Differentiability, integratability. Can we integrate v? Can we differentiate v? Is v continuous? Is v smooth? We load all those assumptions onto v, and it essentially lets us write v as some infinite series. Another thing we assume of v is we assume it can be written as a infinite series of essentially basis functions. Right? And just like we did for the finite difference method, we're going to truncate that series of basis functions. We're going to say, don't use all infinity of them, because I can't manage that. Let's use n of them, right? And so we can then approximate v as those n basis functions. And another assumption we made on v is essentially we can use the same basis functions for our actual solution u. All those assumptions we put on v allow us to make that conclusion, right? So then we have v is equal to a series of coefficients times a series of basis functions, and u is equal to a series of coefficients times a series of basis functions. Plug those in to this initial equation here, calculate the derivatives of my basis functions, calculate these products here, calculate this integral. And then essentially all you need to do is solve for those coefficients, right? The trick, the magic of FEM is that we just assume so much on V that it forces the behavior of those integrals to converge to a nice, easy, answerable solution, so that we can actually just, if we just solve for these coefficients, we can solve those systems. All right, so it just turns into a matter of coefficient hunting, just like if you've ever done the Fourier transform. It's very similar to that. In fact, if you treat it like the Fourier transform and use the Fourier basis function, this turns into a special method called spectral methods. But normally you don't want to do that because that makes the matrices dense. And we like our matrices not to be dense. All right, so the upsides to using FEM is that it has a rigorous mathematical foundation. Very, very rigorous, a huge body of literature, a huge number of software supporting it, and a huge number of applications. It's super powerful. The downsides are you need to be able to understand, well, you don't need to be able to understand this, but in order to understand what you're doing, you need to understand the assumptions you're loading on U and V, right? You need to essentially be able, you need to understand advanced mathematics. You need comfort with functional analysis, right? So I like to think of FEM as like that line about the genie from Aladdin, unlimited cosmic power requires an understanding of functional analysis, which if you're not an applied mathematician, you probably don't have. I don't imagine a lot of you know what a Sobolev space is versus a Hilbert space versus an inner product space, right? And so we're not going to focus a lot on FEM, but that is why so many people use it, is because it's super powerful, but a lot of the time they don't know what's going on under the hood. And this gives you a huge number of those subproblems. You need to do those linear algebras, you need to do those equation solves, you need to be able to integrate. You need to solve those integrals that you get here numerically. And so we'll have a talk on solving those integrals numerically. All right, so, but these three methods, finite element, finite difference, finite volume, are essentially the lay of the land in terms of solving these differential dynamic systems. So now we've got 10 minutes left. I want to essentially give you a worked example. And we don't have to do this right now because I want to open the floor up to questions as well. But I have a paste bin that I will put in the chat that gives you the forward Euler, so that is the stream. Don't click on that. That's what you're in. I'm going to give you this. Paste. There you go. This is the setup for a forward Euler solve to a test problem. All right, and our test problem is this: y prime is equal to some function. That function is in fact equal to the solution, so we can write this as y prime is equal to y of t. And we have the initial conditions as well as the domain we want to solve it on. And this thing has an exact solution, right? What function is its own derivative? Y prime is equal to y. That's the exponential function. So we know the exact solution to this. We can also essentially look at it in MATLAB. All right, so I've got a MATLAB window here. Let me click resume. And I've plugged in essentially all of the initial conditions, all the plotting routines, all the driver functions and all. So all you need to do if you get that code I've given you in the paste bin there to work is essentially to plug in. It didn't take this long even to start up. Plug in the forward Euler method, all right? And so when this loads, I can point to these things. Should have just done it on MATLAB on my machine. I want to hit refresh to make it easier, but that would probably make it worse. So what I've done right now is I've given you the driver. I've given you the loop that will integrate this throughout your entire time domain. I've given you your domain. And I've essentially said, all right, we have a finite a forward Euler step function that takes the previous step, the previous time, and the change in time, and gives you the next solution value. And you need to plug in how you do that in forward Euler. And you also essentially need to plug in that source term. You need to fill those values in through that source term. See if MATLAB is loaded yet. Because right now, when you run this, You do forward Euler driver, starting at 1. Yeah, it's all right. I like it because it's cloud-based. And let's start at time 0, going to time 3, and let's go at a delta t of 0.1. This will currently not work because we're missing our definitions of the forward Euler step, and we're missing our definitions of the source term, which you can plug in. But before we do that, we might not even do it, I want to open the floor up to any questions. And if we don't have any questions, what we'll do is essentially spend the last 7 minutes figuring out what goes in to the forward Euler step. How do I describe that step from one to the next? And then, what do I plug in from that source term? Because we need that source term to give us that f value. But for now, I'll take questions. And this is essentially what, when you call RK4 ODE 4.5, it's doing a version of this, and not forward Euler. It's an extension of forward Euler. It's the Runge-Kutta methods. But this is essentially what it's doing. I'm giving you the tool to essentially integrate this on your own. And you can make a more complicated integration scheme if you like I had to do in grad school. All right. So we'll go till 5. In terms of I'll wait for questions. But until after that, I'll just go ahead and start plugging away in here. So let's get my forward Euler scheme. Slides back up for that. And so my forward Euler scheme for that differential equation was just essentially my next step in time would be equal to, well, we do our algebra, a little bit of algebra here. Let me do that. Once again, I can't draw my slides like I'm used to. We've got our solution at the current time step minus our solution at the next time step divided by delta t is equal to our f, our function, whatever our source term is. And we've given our source term in our problem specification, f of t, y. And in our case, this is just equal to y itself. All right, so we do a little bit of rearranging, and we get that y at the next step. All right, so we got a question here. All right. Oh, yes, okay. So that, I think, is its own discussion outright. But what I usually do is, if I need something to run on a supercomputer, the question is, do I have any thoughts on programming languages for numerical computing? Yes, I have a ton. Right? If I need something to run on a supercomputer and be a compiled language and work in parallel and, behave very quickly because it's a huge system, I'm going to do that in Fortran. But I do not recommend you start in Fortran, because before you code up your algorithm in Fortran, you want to make sure your algorithm works. So my suggestion is prototype your algorithm in a interpreted language like MATLAB or Python. Prove yourself that your algorithm works in a little test case. And then, if you need parallelization, if you need all the bells and whistles of running on a supercomputer, if you need speed, take your algorithm and move it on over to Fortran after you've got it working. So get the test case running in MATLAB or Python, and my recommendation would be MATLAB, because MATLAB is already built. Like, if I need an ODE solver in Fortran, I have to write the ODE solver in Fortran. I've had to write numerical system solvers in Fortran. There are packages, but they don't always do what you want, and they're not packages for everything. If I want to make sure the algorithm works, if I can integrate that ODE or solve that numerical system, I want to write it in MATLAB, because MATLAB has all those functions, right? And so if you're in Fortran writing this thing, you need to write every step needs its own routine that you're probably going to have to write if there's not a library that does it. On the flip side, in MATLAB, there are going to be all those subproblems here. When I talk about subproblems, in Fortran, we have to have a routine that solves each of those subproblems on their own, and we usually are going to have to write those routines. Where are the subproblem things? I had to write a numerical linear algebra routine. We had to write a root finder. We need to write an integration thing, right? MATLAB has every single one of those already built in. So you can just use those to prototype it and say, well, if I can get the numerical integration to work, and I can get the root solver to work, and I get the numerical linear algebra to work, will my algorithm still work, right? Because sometimes algorithms will not work, even if you have all the subproblems solved. So instead of trying to write and debug your subproblems, prototype those in MATLAB, show that your algorithm actually works, and then move it on over to the language for the supercomputer if you need it. Other questions like that, as I sketch our forward Euler scheme outright, we've got yn minus delta t times f of t y. So this is my single forward Euler step. The answer at the next time step is equal to the answer at the current time step minus the time difference times the source term. And in this case, that would just be y. So in our specific problem here, yn plus 1 is equal to yn minus delta t times yn. And so on. And so we can just plug this in as our forward Euler step. MATLAB. Right, MATLAB does have that advantage as well. And there are tools there are smaller communities for Fortran and stuff, but I suggest MATLAB for your prototyping. That's what I prototype in, unless I need it to do text editing and text analysis, in which case Python is what I use for that. All right, so my forward Euler step is just going to be that the next step, y1, is equal to the current time step minus my source term times delta t. And then my source term, that function for our given problem at the very end here, was just y of t. That function was just y. So I'm just going to say f is equal to y in here. And now when I run this, I think I flipped the sign on my derivation. what did I had this working earlier, and then I got rid of all the stuff in it. Let me get rid of that. Let's see, plus f times delta t. Yeah, that seems all looks good. Welcome to Scientific Computing. I'm Dr. Learn. There we go. I got my signs flipped. All right, so then we can see the exact solution, which is the exponential function, with our approximate solution via this ODE integrator. And as we get a little careless, we use fewer points. The accuracy gets lower and lower and lower. And eventually, it just stopped working altogether. Let's use just 1 point. I didn't like that. All right, and as we extend our thing in time, change our delta t. We can see how this system behaves over a wider time domain. And you can essentially see the behavior of your approximate solution compared to your actual solution. As a function of that time. All right, so I will go ahead and end it there. I'll leave a few minutes for questions, but that's about it for today. And I'm not sure what we're going to talk about next time, but as we go through this seminar, as we go through these topics here, we'll be able to fill in the pieces of the puzzle to actually solve these fully dynamical systems. We'll be able to solve those numerical systems. We'll be able to do those finite difference boundary value problems. We'll be able to do those computations, those integrals, be a Monte Carlo technique or what have you. We'll be able to solve those ODEs. And then we can fully model those dynamical systems. But that is it, unless there are any questions. I'll go ahead and wait, until 40 after, 20 till, and then I'll shut down the stream. I don't know how streams work. Absolutely, yeah. And if you guys want to hear anything more about any of the specific topics, like finite volume or what have you, that's something I'm more than happy to do. We can do this kind of forever. There's never a shortage of things to talk about, right? We can even do one on finite element, not the solving of it, because you guys can solve those. I've seen you solve those, right? But what all those assumptions are and the thought process. Because they really load V, that test function, with all of that weight function, with all of those assumptions, and that is how it works. That is how finite element works. And it lets you just turn it into a coefficient hunting. It's just a linear system, if it's a linear problem, that you just solve for the coefficients for, multiply those coefficients by your basis functions, and you've got your solution. I can't see how many people are still here. Let me see if I can get that. Well, that makes two of us at least. And I can make sure you guys have access to the slides if you guys want them. I guess if you've learned nothing else, you've learned that there is a browser version of MATLAB, which you have access to if you have your WSU account, right? You can just go to matlab.mathworks.com and log in with your MathWorks account, which is free to create. Attach that MathWorks account to your WSU account, and then you have access to that online version of MATLAB. Right. So when you say complex, you mean like complicated and not in the complex plane, right? Because you can use linear algebra on arbitrary geometries, right? If I use cylindrical coordinates, I can still use a linear algebra solver for that. The things that change is the form of my differential operators, right? If you think back to Calculus 3, you have those Jacobi multipliers on your integrals and your derivatives. Those will appear in your equations then, right? And then you'll have to essentially take into account those behaviors. Yeah, so you can still use linear algebra for them, absolutely. And yeah, you can actually treat the mapping from a cylindrical coordinate system to a rectangular coordinate system as a as a linear mapping, as a linear algebra problem. Yeah, you can create a multiplier, a matrix that converts your coordinates and your stuff from a cylindrical coordinate problem to a Cartesian coordinate problem to a whatever coordinate problem. All right. So to look up something like that, you might want to look up like grid covariance, linear matrix, and stuff like that, and that'll give you essentially those essentially covariates, not covariance. All right, and that'll give you essentially the conversion between a cylindrical grid and a Cartesian or a polar grid and all the stuff like that. All of these problems you saw, really, they all boil down to linear algebra problems in the end, and the reason for that is because they have so many different points. You pick a small delta t to make it stable. That stability means you have a lot of little points. Each point connects to the other ones. You've got a matrix. Let's see, grid conversion. Right, and you'll see essentially these differential operators will have these additional terms in them that you'll need to have. You essentially need to put those in a matrix and multiply it, or handle them explicitly. All right, well, last call for questions. I'll wait another couple minutes, and then we're done for today. See you all in 2 weeks. Look at this nonsense. Who comes up with this stuff? View by clicking. Yeah, sounds good. I don't know what that is, but it'll be something relatively basic so we can start at the ground floor. All right. Everybody take care.